Hi, everybody. Thanks for coming to this presentation. Today we'll be talking about the optimization of threshold functions over streams, in particular stream joins. My name is Walter Tsai, and I'm very pleased to present this collaboration between Microsoft Research and the University of Washington. Let's take a look at our motivating example. In this scenario, we have an industrial manufacturing equipment plant filled with machines. And what we want to avoid is condensation forming on the surface of these machines. Condensation might lead to the product being ruined or possibly just corrosion. Either way, we want to make sure that we avoid this situation. Now, luckily, we don't have to point a camera at every surface and try and make out the little glints that might be water droplets. Instead, we can get away with using three relatively rudimentary sensors. In particular, an air temperature sensor, a surface temperature sensor, and a relative humidity sensor. These three readings can then be combined and plugged into something called the Magnus formula, which we present here. If the Magnus formula comes back with a value greater than 0, aka if it crosses a threshold, then we know that condensation might be forming on some surface, and we should trigger an alarm and alert the important individuals. What happens in the naive setting is that each of these different sensors will package their readings together with a timestamp to produce a timestamp tuple. Each of these timestamp tuples will then be emitted from the sensors on independent data streams. Each of the independent data streams will then be consumed and combined by some central processing node, a data stream management system, which will then run those now triple length tuples through our threshold function. Because the data sensors are independent, they don't control each other, the streams will have to be temporally joined, aka they're joined on that timestamp. And again, because there might be some time drift between those sensors, there has to be some margin for error, aka the data stream management system, the central processing node, will have to employ an interval join. Now, what this means is that, say, 2 tuples, or in this case, 3 tuples, if all their timestamps are within some delta of one another, that means that they can be legally packaged together, and that new triple will be delivered to the threshold function. Our primary observation here is that for quasi-convex functions, as the Magnus formula is an example of this, we don't have to actually manage all these different triples because that can be very costly. Instead, we can just drop some. In fact, we can even drop some base tuples. They never even need to enter the system to begin with. We're going to take the next few slides to explain this. Now, why is this expensive? Why is this such an important question? In order to illustrate that, let's take a look back at our motivating example. Again, we have 3 streams illustrated below with time running from left to right. Those streams again are S, H, and A. Now, suppose that stream S lags behind H and A. Before that happens, tuples will be coming in at a relatively steady pace. Again, because the streams are independent, there might be some out-of-order behavior. And all of a sudden, the S stream will halt. Well, what must the data stream management system do? It'll have to cache all the tuples still flowing in from streams H and A. As the longer S stays down, the more tuples the data stream management system will have to store. With enough tuples, the data stream management system might run out of memory. It might completely fail. We're now going to illustrate how the insight for quasi-convex threshold functions will allow us to limit that state saving or that state storage. Before we can reap all these state savings benefits, what we need to do is we need to understand what a quasi-convex function is. Well, given a function g, let's assume that's quasi-convex. That means that for any 3 inputs, x1 less than x2 less than x3, g applied to that middle value, x2, will be less than or equal to the maximum of those 2 outside neighbors, x1 and x3. This is a very broad class of functions. Step functions, linear functions, positive quadratic. It's quite liberal. And importantly, what this implies for threshold functions is that if x2, that middle value, successfully triggers the alarm, we know that at least one of its neighbors on the outside, x1 or x3, at least one of them will also trigger the alarm. So in some sense, that middle value, x2, becomes superfluous. Let's take a look at what quasiconvexity will imply in the streaming scenario. In this setup, we only have two streams, S and R. Again, time is measured from left to right. And for tuples on the S stream, we depict value, aka the actual reading that we fed into the threshold function on the vertical axis. Now, if we start with a tuple from R, in this, shown in this picture as little r, we know that little r will have a window of valid join partners, which we depict here as the triangle projected from little r onto the stream S. Inside this window, we find 6 valid join partners. We are going to focus on this little tuple here, little s. Now, you'll note that s is not the min or the max. They're here. So, as far as little r is concerned, s is superfluous. How do we know this? Well, if we map back to our original picture, the min maps to S1, the max maps to S3, and little s is that superfluous, unnecessary middle value. If the tuple RS will trigger an alarm, we know that at least one of the min and the max, when joined with little r, will also trigger an alarm. Now, the problem is that in this very simple scenario, S can simply omit little s and we'll be fine. But S doesn't have control or even knowledge about the tuples from stream R. You'll recall in our previous scenario, they might be lagging behind and they will only catch up later. So this is difficult because little r might not actually be here. In fact, it might have slid over here, in which case stream S would actually need to hold on to little s. Despite this complication, we have the intuition that the existence of certain neighbors, tuples within the same time window, could allow us to omit other tuples. Let's take a look at what that condition might look like. Let's try and omit S again. The first thing we need is a pair, S1 and S2. S1 and S2 have to occur on both sides of S temporally, but their distance can be no longer than the length of an interval. And finally, their values must both be above S. We call this an above pair or above bracket. Similarly, we need a pair below, S3 and S4. Again, we have the same conditions. The only difference is that their values must be below S. This is now a below bracket, and we can say that S is bracketed. You'll note that if there is some tuple, little r, that joins with S, no matter where r lands, we know that there must be at least one tuple from both the above and below bracketing pair that also joined with S. Thus, no matter where R lands, S is superfluous, under the condition that S joins with R. Let's take a look at what this then implies for our motivating example. Again, S has stopped working, and we have to back up all these different tuples from H and A. Instead of backing up all these different tuples, caching them, we only have to store a small fraction. Excellent. Obviously, omitting tuples based on bracketing neighbors is a local, greedy optimization. It's local to a particular stream, completely independent without any knowledge from any joining streams. However, we prove that it is globally optimal, and then it generalizes to both the multi-stream and multi-query setting. Moreover, our evaluation reflects that theoretical optimality. In conclusion, we encourage the audience to please read the full text of our paper and to forward us any questions you might have. I'd like to have a big thank you to Microsoft Research and the University of Washington for making this project possible.